It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, so we're going to end our unit on exponential functions here by jumping into lesson 8. Also at this point you're going to need your calculator out, so it's time to reach into your bag and grab out your calculator or open up your Chromebook to get your calculator out, and we're going to pause the video until everyone's good to go, and then we can hit play and we're ready to get started in lesson 8. So we're going to be comparing linear functions from November and exponential functions that we've been talking about for the month of December. So let's start by comparing linear and exponential functions. So linear functions we'll put over here, and over here we'll put exponential functions. So exponential functions, the key idea is we're working with repeated multiplication. We're repeatedly multiplying by the same number, times 2 times 2 times 2 times 2 times 3 times 3, whatever that number is. Then for linear functions, it's not repeated multiplication, it's repeated addition or subtraction. Linear functions are repeated addition, which is also known as the slope, which is also known as the constant rate of change. So exponential functions are all about repeated multiplication, whereas linear functions are all about repeated addition. Linear functions, we know from last year and this year, are in the form of y equals mx plus b, where m is the slope and b is the y-intercept. Then, for exponential functions, their equations look different. Their equations look like a, our starting amount, whatever I'm starting with, my initial value, times my multiplier to the x power. Our variable is in the exponent for exponential functions. So for linear functions, it's y equals mx plus b, and for exponentials, it's y equals a times b to the x. When we graph these, well, the graphs of linear functions, guess what those are? When we graph linear functions, we get lines. That's why we call them linear functions. This one has a positive slope because it's increasing. This one has a negative slope, less than 0, because it's decreasing. The graphs of exponential functions are a lot more interesting. The graphs of exponential functions here are a lot more interesting. They start off really flat and then quickly skyrocket up. And remember, we talked about how they never touch. These exponential functions never touch 0. They get really close to 0, but they never actually intersect the x-axis. So here I have exponential growth. Why? Because it's increasing as I read left to right. So this tells me my multiplier is bigger than 1. 1.5, 1.75. 2, 3, 4, any number bigger than 1, that's my multiplier, will cause me to have exponential growth and look like this graph here. Or I could be dealing with exponential decay. That looks very similar. It starts up high and then plummets down really quickly. And again, never touches the x-axis. It gets really close to it, but never touches it. So this is a decay function. And my b value is less than 1. And instead of being greater than 1, my b is less than 1, but it can't go negative. So numbers like 0.5, 0.93, any number smaller than 1, 2/3, any number between 0 and 1 will cause me to decay. And one nice little vocab word we learned this unit, that line that we get really close to, that horizontal line, is called an asymptote. I can get really close to it, but I can't touch the x-axis there, and all exponential functions behave like that. So this is a good little overview, a good way to study to get your brain in the mind of exponential and linear functions. Repeated addition or repeated multiplication. What do their equations look like? And graphically, what do they look like? So we'll do a couple problems working with linear and exponential functions, and we'll call it a day. So our friend Michael here has $10 in his savings account. Ouch, he's got some work to do there. He's only got $10. Option 1, so let's read through option 1. Option 1 adds $100 to his account each week. So let's think about this. Option 1 here. Each week, 100, 100, 100, 100. This seems pretty linear to me, right? Each week we keep adding, there's the keyword there, we keep adding 100. So linear equations look like y equals mx plus b. So in this case, it's y equals m. I keep adding 100. And my y-intercept, my initial value is 10. So that function there, write a function that models each option. So there's option 1. And option 2 is an exponential function. Option 2 is an exponential function, and those look like y equals a times b to the x. So let's read through option 2. Option 2 will double. There's the keyword there. Option 2 will double. That's what makes it exponential, is that doubling there. Option 2 will double the amount in his account at the end of each week. All right, so y equals, a is my starting amount. I'm starting with $10. And what keeps happening to that? Well, it keeps doubling, so my multiplier is 2 to the x. You can't make that 20. You can't multiply those two together. Leave those two numbers as they are. So those are my two functions. One's linear and one's exponential. One's repeated addition and the other's repeated multiplication. Michael wants to have at least $700 as an account at the end of 7 weeks to buy a mountain bike. Great. I hope Michael gets his mountain bike because I want Michael to enjoy biking around on the mountain. So which option will enable him to reach his goal? Well, 7 weeks, I'm just going to plug that in. Just going to plug in 7 weeks here. 100 times 7 plus 10. Hopefully you can do that in your head, is 710. So does that let him reach his goal? It does. He can buy his bike. This next option, let's plug it on into our calculators. 10 times 2 raised to the 7th power. How about I hit the right button? Raised to the 7th power is 1280. 1280, there we go. Does that work? It does. So I'd pick option 2, but that's not what it's asking. It's asking him which will let him reach his goal. The answer is both of them. Both of them will let him reach his goal. Number 2, determine if a linear, repeated addition, or exponential, repeated multiplication, can be used to model the table below. So we always check, is it linear? Linear is easy to check because I look at what do I add, or what do I subtract. 20 to 30 is 10, 30 to 45 is 15. This isn't looking good because all of these are plus 1. So right there, it's not linear. It's not a linear function because there's not a constant rate of change. There's no constant rate, there's no Crocs. It's not wearing its Crocs today. There's no constant rate of change. So is it exponential? What's my multiplier? 20 times what gives me 30? 30 times what gives me 45? What's my multiplier? 20 times what gives me 30? Well, instead of subtracting, we're going to divide to figure out what that common factor is. Well, 20 times what is 30? Well, it's 1.5. 30 times 1.5 is 45. So my multiplier, my b value is 1.5. I keep repeatedly multiplying by 1.5. So y equals a times b to the x. So what represents this table? Y equals 20, it's my starting amount, times 1.5 raised to the x power. And that right there is my equation for this table. It's not linear because there was no constant rate of change. So I had to figure out my multiplier. And I figured out my multiplier by dividing. So about a year ago, Joey watched a video about a band and noticed it had 843 views. So there it is right there. 1 month later, he had 1708. And Joey kept doing that. He kept every month. Notice those are all +1, which is good. He kept keeping track of how many views the video had. Should Joey use a linear, repeated addition, or exponential? So let's check, is it linear? Is this function linear? Well, what do I need to add? So to figure out what I need to add, I actually subtract. 1708 minus 843, and we get, what do we get? 865. So this was plus 865. Well, what about the next month? That looks like, doing some mental math here, plus 1807. Well, I'm going to call it quits right there. It's not linear. It's not linear. There is not a constant rate of change. It's not repeated addition. There's not a constant rate of change. There's not a croc. Constant rate of change. There's not a constant rate of change. So Joey should use an exponential. Didn't ask us to write it. It just said, which one should I use? And it's definitely not linear because there's no constant rate of change there. It's an exponential function. There appears to be repeatedly multiplying here. Okay? Number 4, the population in the country of Oz. So we're in the Wizard of Oz here, everyone's favorite movie, Somewhere Over the Rainbow, the Munchkin Land. So pretend we're in Munchkin Land right now. The population is expected to grow. Population is growing by a factor of 5%. So this is what we dealt with on Tuesday and Wednesday this week. Or for you guys, it was what? It was Wednesday and Thursday. We grew by a factor of 5%. So we take that 5% and turn it into a decimal, right? 0.05. And because it's growing, I do 1 plus. So this population is exponential because it's growing by a percentage. It's growing by a percentage, so that makes it an exponential function. So it says write a formula to model the population. So the population equals what? Well, there were 600,000 people in Oz. And my multiplier, how do I grow by 5%? Well, whenever I grow by a percentage, that's an exponential function. And we said it's exponential because it's growing by a percentage. There's a common factor to grow by 5%. However, the annual food supply in Oz is currently sufficient for a population. They can only feed 700,000 people. And it increases at a rate of an additional 10,000 people per year. So right now they're at 700,000 and they can just keep adding 10,000, 10,000, 10,000. So this sounds linear to me. My food supply sounds linear. So this is going to be y equals mx plus b. What's my rate of change, my slope? Well, it's 10,000 every year. And I started at 700,000 people I could feed. So there's my food supply formula. So my population's growing exponentially. My food supply is growing linearly. Eventually, does my population exceed my food? Am I going to be unable to feed all the munchkins in the land of Oz? It'd be rather unfortunate. So the way that we're going to do that, we're going to go to y equals. We're going to go to our table. So you're going to pull out your calculator and you're going to go to your table. And whenever I want to go to my table, I got to get the equations into y equal 600,000 times 1.05 raised to the x. 'Cause I don't have a t. And then I have 10,000, 1, 2, 3, x plus 700,000. And if I go to my second table, I'll be able to see, I don't need negative numbers here, how many people are in Oz and how much food I have. So notice I have more food, more food, more food, more food. I'm still good. Oh, look at year 5 here. I have more people than I have food. So unfortunately, some of them are going to starve off. How sad. How sad that we're going to lose a couple thousand munchkins. So at year 5, that's when my table here finally shows the exponential winning. So let me label this. This is population, and this here is food. Population and food. So when does it happen? At year 5. T equals 5. That's when the population finally beats the food. All right, number 5 here. Hopefully you're still with me. Hopefully I didn't lose you, and hopefully you're not snoozing. Here's a table. 2 points, that's it. If it's exponential, so that's repeated multiplication. So we're going to pretend there's a multiplying pattern here. How do I go from 150 to 450? Well, that looks like a times 3 pattern to me. So if we're exponential, let's write the equation. Y equals my starting amount, A, times my multiplier, which in this case would be 3, right? 3 times 150 is 450, to the x, or to the t power here. That would be the exponential function. And now we're going to do it all again. Let's pretend we never did that, and let's pretend we're working with a linear function here. So linear functions are repeated addition. So what do I add to go to from 150 to 450? Well, I add 300. So that's my slope, that's my rate of change. y equals my rate of change, mx, or in this case t, mx plus my starting amount, plus 150, mx plus b. And that's the equation on my line. So notice between any 2 points, and we'll talk about this in your remote assignment next, any 2 points you can make a line or you can make an exponential. Linears if we're looking at it through an addition viewpoint, exponentials if we're looking at it through a multiplicative relationship or through multiplication. And finally, we're going to jump to number 2 on this homework page here at the bottom of 34. I'm not giving you guys homework tonight, but I do want to quickly talk through number 2 here. So for each of the following, determine if it's linear or if it's exponential. So let's pause the video, and you've got 1, 2, 3, 4, 5, where you're going to write it's linear or it's exponential, and then we'll unpause and talk through these solutions. So here we go. The value of a house increases by 1.5% each year. Well, I'm increasing by 1%. So that's a multiplier. I have a multiplier of, well, I made it a decimal, move it twice, and it's increasing, so I'm going to do 1 plus. That's my multiplier. So this tells me I'm working with an exponential function. Whenever I grow by 1%, that means I'm working with exponential functions. All right, the teacher, I have a great typo of mine. The teacher deducts 10 points each day for which an assignment is late. Well, minus 10, minus 10, minus 10, minus 10, that's a linear function with a slope of negative 10. I keep subtracting 10 points each time. Every hour I'm left with a third of the bacteria dies. So that's dividing by 3, right? A third, divide by 3, divide by 3. That's totally exponential. I'm not adding or subtracting the same number. I'm taking a fraction, a third, a third, a third of what's left. A population of bacteria doubles, or there's the bad word, it doubles. This is exponential. And finally, a vine grows by 6 centimeters each week. Well, it's growing by 6, so plus 6, plus 6, plus 6, plus 6. This here would be linear. Every time, each week, I keep adding 6. So again, linear functions are repeated addition. Exponential functions are repeated multiplication. And I'll see you guys sometime soon.